So let's talk about motion. I'm going to draw a graph or a function that represents an object's position or current position in relation to its starting position over some time period. So let's say I have a function that looks something like this. So again, S of t represents the distance from your starting position. We want to be able to interpret what this graph is telling us about this object. So let's say we're starting at 0, 0, this origin. We'll say that this is t sub 0, and that is actually at time equals 0. As we move along this function, you'll notice that the outputs are initially increasing in value. And if the outputs represent the distance from your starting position, then we know as we're moving along the curve for this first portion that we are increasing our distance away from our starting position until we've reached this point here. And this maximum represents the farthest distance away from our starting position in the particular direction that we are currently traveling. As we move back down the function curve, the outputs start to decrease, which means our distance from our starting position is getting smaller and smaller and smaller until we've reached this x-intercept. This x-intercept has an output of 0, which means our distance from the starting position is 0, and therefore I am back to the starting position. And that occurs at this end piece as well. So these two x-intercepts mean we're back at the starting position. When the graph goes negative, all that means is that we're traveling away from our starting position, but in the opposite direction. And this minimum down here is the farthest point away in the opposite direction. Now, as we moved along this function curve, our distance was changing over time. And we're going to be interested in how that rate of change, or how to calculate that rate of change. Calculating the distance over time will get you velocity. So velocity we'll call v of t is going to give us the instantaneous rate of change of our position. Instantaneous rate of change, we have learned, represents or is synonymous with a derivative. So we know velocity is equal to the derivative of our position. Now, we may also be interested in just calculating average velocity. We may just want to ask, over the course of some time interval, on average, how quickly are we moving? And in that case, we're just going to calculate the average rate of change of our position. So to calculate an instantaneous rate of change of position, we're calculating a derivative. Average rate of change of a position, we're just going to take the change in y over the change in x. So we are doing the difference of our position over the difference in time. The change in your position, this top portion of the average rate of change, when you calculate change in position, you are calculating what's called displacement. Okay, so if you're asked to find the displacement of the object over some time, you're just calculating the change in its position. If we go back to our position graph, we can look at some aspects of velocity and other questions arise, or other conclusions can be drawn. As we move along our function curve, our velocity is positive. But as we're moving along our function curve, for this first part anyway, we also notice that the velocity is not constant, meaning the velocity values are changing. In fact, they're decreasing up until the point where they reach this maximum, and we have a horizontal tangent, which means our velocity is equal to 0. And if the velocity is equal to 0, meaning there is no rate of change, then we know the object is at rest. So if you need to know when an object is at rest, that means it is not moving, and the velocity should be equal to 0. Now, because velocity is also changing, we would be interested in calculating the rate of change of velocity. The rate of change of velocity is acceleration. Which we will call A of t. And this is the instantaneous rate of change of velocity. Acceleration is the rate of change of position. So acceleration is your derivative of velocity or your second derivative of position, because it is a rate of change of a rate of change. When it comes to labeling things, we know position, we are just going to assign some distance. For velocity, we're doing distance over time. For acceleration, we need distance over time because we want the rate of change of the rate of change, which means distance over time squared, because dividing by time is the same thing as multiplying by 1 over time, and that's why you have distance over time squared. So this is all in reference of our labeling for our answers. So labeling velocity, acceleration, and position. Now, what does acceleration help us determine? Well, if I know velocity and I know acceleration, I'll just get rid of this whole thing, then I can determine whether or not an object is speeding up or slowing down. And what I have to consider when answering that question is that velocity and acceleration are vectors. So these are vector quantities, which means they have a magnitude, but also a direction. And if I know velocity and acceleration are going in the same direction, then my object should be speeding up. And they will be going in the same direction if they have the same sign. So velocity and acceleration have the same sign at some point, t. So we'll say at t equals c. Then, actually, let's just say at some time t. Then the object is speeding up. But if they have different signs, then the object is slowing down. So if your velocity is going in one direction and you're accelerating in the opposite direction, that implies that you are decelerating and therefore slowing down. So comparing the signs of acceleration and velocity at a certain point in time can tell you if the object is speeding up or slowing down. And now, building off the fact that velocity is a vector and it indicates direction, and I can also determine when the object changes direction by looking at the signs of our velocity. So velocity, again, being a vector, indicating that it has direction, means that we can determine where we have a change in direction. And we are going to do that by analyze a change in sign. So you're looking for going from positive to negative or negative to positive. So going back to our position function, we said that as we climbed along this function curve that output a position in relation to its starting position, when we got to that maximum, we said that this was the furthest point away. And now knowing that velocity is a vector and it can tell you when you change direction, it should make sense. Because when I look at the velocity or the slope of the tangent lines leading up to that point, they were positive. Then they went to 0, indicating the thing was at rest. But then the velocity went negative, meaning I've changed direction. And it makes sense when I look at what this function outputs. The output is distance from the starting position. So distance was originally increasing and then decreasing. So that aligns with the fact that the sign for velocity, or change in sign of velocity, can tell you when an object has changed direction. To conclude the video, we'll talk about speed. So we may not be interested in what direction we're going, but rather how fast we're going in general. And that would be a question about speed. Speed is not a vector, but rather a scalar, meaning all it has is a magnitude, no direction. So when I say how fast are you going, you may say 40 miles an hour, but that is not indicative of what direction you're going. So velocity would say 40 miles an hour in a certain direction. So what's the difference between speed and velocity? The fact that there's no direction associated with it. And therefore, to calculate speed, all we have to do is take the magnitude of our velocity, or the absolute value of velocity. And that is how we get speed. And that is an introduction to motion in relation to position, velocity, and acceleration.